It is January 2023. The city is Beijing. Outside, winter has settled over the Peking University campus, with the particular cold that belongs to northern China in the dead of the season. Dry, still, the kind of cold that makes the air feel thinner than it actually is, that makes the space between buildings feel somehow larger, as if the temperature itself is stretching the distances. The Wyoming Lake on campus has a skin of ice across its surface. The trees along its banks stand bare and skeletal against the orange ambient glow that hangs over every Chinese city at night. That combination of streetlights and commerce and 10 million windows that never quite goes dark. Inside the Department of Earth and Space Sciences, the lights in one particular office have been on for several hours. The building around it is quiet at this time of night. Footsteps somewhere down a corridor, the low hum of a ventilation system doing its work, the occasional distant sound of a door. Small, ordinary sounds, but inside this office, even those sounds feel distant, irrelevant, because the two people sitting here have stopped noticing them. Yi Yang and Zhaodong Song are seismologists. They study the behavior of seismic waves, the energy that propagates through the earth during earthquakes, traveling through layers of rock and mineral and metal and molten iron, carrying information about the deep interior outward to sensors placed on the surface. Their work is methodical, careful, the kind of science that proceeds in small increments across years and decades, accumulating data slowly, building a picture of a place that no instrument has ever physically reached and no human will ever visit. Tonight, they are reviewing something that should be routine. They have compiled a dataset spanning decades, seismic wave records going back to the 1970s, drawn from earthquakes that occurred repeatedly near the same locations, generating similar bursts of energy that traveled along the same interior pathways at different moments in time. When you compare the waveforms of similar earthquakes from the same source region over many years, tiny shifts in arrival time and in the shape of the waveform reveal whether the inner core has rotated relative to the surface above it. It's a technique that has been refined over 30 years. It is the primary tool seismologists use to study the behavior of a place they can never reach. The data on the screen goes back to the 1970s. Earthquake pairs, waveform comparisons, arrival time measurements. The 1970s look right, the 1980s, the 1990s, the early 2000s. Then something changes. The signature, the characteristic, consistent drift in the seismic waveforms that indicates the inner core has been rotating slightly faster than the planet above it. Flatten. The drift that has been moving in the same direction, year after year, for decades, simply stops progressing. The signal stalls. And, in the most recent years of the dataset, the measurements from the 2010s and early 2020s, the signature appears to have begun moving in the opposite direction. Yi Yang sets down her pen. Zhaodong Song is very still. Neither of them speaks. 5,000 kilometers beneath the campus of Peking University, beneath the ice on the lake, beneath the frozen soil, beneath hundreds of kilometers of mantle rock, beneath the churning liquid outer core. The iron heart of this planet appears to have changed what it is doing. Not suddenly, not with any detectable violence or warning. Quietly, over years, the way fundamental things change when no instrument sensitive enough to detect them is watching. Until now, they are the first people in history holding data clear enough to show it happened. The data looked routine, until they laid 40 years of it side by side and realized the rotation had stopped. Welcome to Galaxy Pulse, where we go past the press release, past the reassuring headline, and into the part of the science that makes people go very quiet. If you found your way to this video, you probably already caught something in early 2023 about Earth's inner core. Maybe you saw the headline. Maybe you read a summary somewhere that said scientists had confirmed the inner core's rotation had paused, possibly reversed, and then immediately explained that it's a natural cycle, nothing to worry about. Everything is fine. And here's the thing. Most of that was true, as far as it went, but accurate and complete are two different things. The parts of this story that got left out are exactly the parts that deserve the most attention. The parts that don't fit into a reassuring 3-paragraph summary. The parts that are, frankly, more interesting than the headline version, and more sobering, too. Before we go any further, drop a comment below. I read them. Tell me what unsettles you more, what's happening out in space, or what's happening directly beneath your feet, because tonight we are not going outward. Tonight we go straight down, 5,000 kilometers through rock and metal and fire, into the engine room of this planet, to ask why that engine appears to have changed gear, and what that means for everything we've built on top of it. If you want to be here when the next video drops, hit subscribe. We do this series differently from most science channels. Now, let's get into it. This is not really a story about geology. It's a story about rotation. About a sphere of solid iron the size of the moon, sitting at the very center of this planet, spinning at its own rate, slightly faster than everything above it, like a gyroscope nested inside a larger gyroscope. That differential spin is not a geological curiosity. It is not a footnote. It is part of the mechanism that makes this planet livable. It is connected, through a chain of physics we are only beginning to understand in detail, to the magnetic field that surrounds Earth and deflects the solar wind. That constant, powerful stream of charged particles from the sun that would, over geological time, strip away the atmosphere of any planet left unshielded. Earth, without its magnetic field, looks something like Mars. With it, we're here. In early 2023, a peer-reviewed study published in Nature Geoscience, one of the most rigorous scientific journals on the planet, concluded that the inner core's differential rotation had effectively paused around the year 2009, and the paper proposed that the core may now be in the early stages of reversing direction relative to the surface above it. Scientists publicly called this normal. The paper's own data tells a more complicated story. So, what exactly does it mean for a planetary core to stop its differential spin? If the inner core is electromagnetically coupled to the outer core, and the outer core generates Earth's magnetic field, what happens to that field when the coupling changes? Why did this happen around 2009, and why are most people only hearing about it now, more than a decade later? Is this part of a regular cycle that Earth has always gone through quietly? Or is this cycle different from the ones that came before, because the world sitting above it is different? And what do the scientists working most closely with this data actually believe about the implications, versus what they're comfortable saying publicly? This is not a doomsday video. I want to be explicit about that before we go further. The inner core changing its rotation rate does not mean a major earthquake is coming tomorrow. It does not mean the magnetic poles will flip next week. Neither of those is a reasonable reading of the evidence, and we are not going there. What it does mean is that something we thought we understood, something we built our entire theoretical model of this planet's magnetic protection around, did something we did not predict. Something that our instruments only recently became sensitive enough to detect. And once you look at the complete picture, the seismic waveform data, the magnetic field satellite measurements, the global GPS records of day length, the emergency out-of-cycle update to the world magnetic model, the nothing to worry about, it's just a cycle, framing starts to feel like it's carrying more weight than the evidence fully supports. Stay with me tonight, because the implications of what's happening 5,000 kilometers beneath your feet reach considerably higher than most coverage has acknowledged. To understand why any of this matters, we need to begin at the beginning. We need to understand what the inner core actually is, how we know anything about it at all, why its rotation was considered one of the stable, reliable features of a dynamic planet, and what it actually means when a stable thing stops behaving the way the models said it would. Because the strangest part of this story isn't that the core paused. The strangest part is what we had been assuming about it for decades without realizing we were assuming it. Most of us learned the basic structure of Earth sometime in school: a diagram, layered, symmetrical, color-coded, crust on the outside, thin as the skin of an apple relative to the whole, mantle beneath that, thick, slow-moving, technically solid, but behaving plastically over geological time, then the outer core, then the inner core at the very center, 4 layers, clean, orderly. The sort of diagram that implies we understand the thing it describes. We don't, not fully, and the gap between what the diagram suggests and what we actually know is where this story lies. Start with the outer core, a shell of liquid iron and nickel sitting roughly 900 kilometers below the surface. About 200 kilometers thick. Temperatures between 4 and 5,000 degrees Celsius. It is not molten in the way that most people imagine molten, like lava, thick and slow, glowing orange. It's a conducting fluid under extraordinary pressure, churning in convective patterns driven by heat from below and the spin of the planet above. As that conducting fluid moves, it generates electric currents, and those electric currents generate Earth's magnetic field. This process is called the geodynamo, the mechanism by which a rotating, electrically conducting fluid produces and sustains a planetary magnetic field. The same fundamental physics as a dynamo in a hydroelectric plant, operating at a scale that makes any human engineering feel small. Now, go deeper still. At the center of the outer core, under pressure that is almost impossible to intuit, sits the inner core, a sphere of iron and nickel with a radius of roughly 440 kilometers, approximately the size of the moon. The temperature at the very center of Earth is estimated at 5,000 to 6,000 degrees Celsius, comparable to the surface of the sun, and yet it is solid. Not because it has cooled. The inner core is not cool. It is as hot as a star's surface. It is solid because the pressure is approximately 360 gigapascals, 6 million times the atmospheric pressure you feel standing outside. At that pressure, iron cannot remain liquid regardless of the temperature. The atoms are forced into a crystalline arrangement by the sheer weight of everything above them. The inner core is a ball of solid iron crystal, sitting inside a shell of liquid iron, at temperatures that would vaporize any material we've ever held in our hands. And we only confirmed it existed in 1936. The woman who figured it out was Inge Lehmann, a Danish seismologist working with data from a large earthquake near New Zealand. She noticed something in the records that didn't fit the existing model. Seismic waves that should have been deflected away by the outer core were arriving at recording stations at angles and times that made no sense, unless there was a solid sphere at the center, a boundary, an inner body inside the outer shell. She published her conclusion in a paper that was 2 pages long. It changed our understanding of this planet permanently. But Lehmann's discovery only established that the inner core exists and is solid. It said nothing about what it does over time. Specifically, it said nothing about whether the inner core rotates at the same rate as the planet around it, or at a different rate. That question, which turns out to matter enormously, wasn't seriously addressed until the 1990s. The technique that made it possible is elegant in its indirectness. When earthquakes occur at similar locations multiple times over years or decades, they produce nearly identical seismic signals that travel through the same interior pathway. If the inner core has rotated between those 2 earthquakes, even by a fraction of a degree, the wave path through the anisotropic crystal structure of the core is slightly different. The waveforms shift, arrival times change, not by much, by fractions of a second, but consistently, measurably, reproducibly. In 1996, Xiaodong Song and Paul Richards at Columbia University published a landmark paper in Nature. Using exactly this technique, they showed that the inner core was rotating faster than the surface above it. The superrotation, the eastward spin of the inner core relative to the mantle and crust, appeared to be around 1 degree per year. Later analyses revised that number downward considerably. The current best estimates hover somewhere between 0.1 and 0.5 degrees per year, depending on the dataset and the analytical method. But the direction was consistent across independent research groups. The inner core was spinning eastward, slightly faster than the planet above it. For the 2 decades after that 1996 paper, this was the baseline picture. The inner core superrotates. That's what it does. The electromagnetic torque from the convecting fluid outer core drags it forward slightly relative to the mantle. The physics supports it. The observations support it. It goes in the textbooks. Think of it this way. Imagine a gyroscope, one of those precision spinning tops used in navigation systems, balanced and spinning with extraordinary stability, enclosed inside a sealed container filled with thick, electrically conducting fluid. The gyroscope spins at its own rate. The fluid transmits forces between the gyroscope and the container walls. Change what the fluid is doing, and the gyroscope responds. Change what the gyroscope is doing, and the fluid responds. The outer container responds. Everything is coupled. Everything exchanges forces with everything else, and the state of the whole system at any moment is the product of all those couplings playing out over time. Earth's inner core is the gyroscope. The fluid outer core is the conducting medium. The mantle and crust are the outer container. For decades, measurements said the gyroscope was spinning slightly faster than the container. That was the stable, reproducible, well-supported picture. Now, the 2023 paper, Yang and Song, assembled the most comprehensive dataset of repeated earthquake waveform comparisons ever compiled for inner core rotation studies. 50 years of data. Earthquake pairs from multiple source regions around the globe, the South Sandwich Islands in the South Atlantic, which produce unusually frequent and geologically similar earthquakes that have become invaluable for this kind of work. Events in the Arctic, events in the Pacific. The dataset was larger, more carefully curated, and more systematically analyzed than anything that had come before it. The pattern from the 1970s through roughly the mid-2000s was consistent with everything previously published. The seismic signatures showed the familiar eastward drift. The inner core was doing what decades of research said it should be doing. Then the drift flattened. Around 2009, the differential seismic signature stopped progressing. Earthquake pairs, spanning the late 2000s onward, no longer showed the systematic waveform shift that indicated ongoing superrotation. The signal that had been moving in one direction for decades went still. And in the most recent years of the record, it appeared to move in the other direction. Yang and Song didn't publish this immediately. They checked. They examined whether the apparent change in the seismic signature could be explained by changes in instrument calibration at recording stations. They looked at whether the earthquake locations themselves had shifted, since changes in source location could produce apparent waveform changes that had nothing to do with the inner core. They tested whether tectonic changes in the crust near source regions could explain what they were seeing. They compared their primary dataset against secondary datasets using different source regions. Each alternative explanation was tested. Each failed to account for the observed pattern. The conclusion: the superrotation had stopped around 2009. Now, here is where most coverage of this story got oversimplified. Because understanding what stopped actually means in this context requires understanding how the measurement works at a physical level. Seismic P waves. The compressional waves used in this technique travel fastest through the inner core when they move parallel to Earth's rotation axis, from geographic pole to pole. They travel slower when they move equatorially. This directional dependence, anisotropy, exists because the iron crystals in the inner core are not randomly oriented. They are aligned preferentially along the polar axis. Probably as a result of the way the inner core grew over billions of years of crystallization at the bottom of the liquid outer core. The alignment is not perfect, but it's consistent enough to produce a measurable directional effect on wave speeds. When the inner core rotates, that aligned crystal structure rotates with it. A seismic wave that previously traveled along a path that was, say, 30 degrees from the pole alignment now travels along a path that is 31 degrees from it, because the alignment has moved slightly. That tiny difference produces a tiny but measurable change in arrival time and waveform shape. When Yang and Song found the waveform signatures flattened, when the differential shift stopped progressing, what they were observing was the cessation of that crystal structure rotation relative to the surface. The inner core, as a whole-oriented structure, had stopped moving relative to the planet above it. That is not a small result. The inner core's rotation is electromagnetically coupled to the fluid outer core above it. The outer core's fluid motion generates Earth's magnetic field through the geodynamo process. Changes in inner core rotation alter the electromagnetic coupling at the inner core boundary, the boundary between solid inner core and liquid outer core. Changes in that coupling affect the patterns of fluid motion in the outer core. And changes in outer core fluid motion affect the magnetic field the fluid generates. The inner core didn't just pause a geological curiosity. It changed a boundary condition of the system that generates and maintains Earth's magnetic shield. And the magnetic field, as we are about to see, had already been showing exactly the kind of changes you would expect if that boundary condition had shifted. If the seismic data had been the only evidence, one research group's result, contested in the journals, confined to a specialist debate, the story might have stayed contained. Interesting internally, not world-shaking externally. But then, researchers started comparing the timing of the inner core's deceleration to something that an entirely different set of instruments, using entirely different physics, had been recording at Earth's surface for decades. Changes in the length of the day, and the two datasets matched. Chapter 3. The surface is already responding. Let's begin with something that sounds like it shouldn't be scientifically relevant. The length of a day, not the 24 hours on the clock. Not the social, rounded, convenient approximation we use to organize our schedules and set our alarms. The actual, precise, physical duration of one complete rotation of Earth relative to distant astronomical reference points, measured continuously, with extraordinary precision, by a global network of atomic clocks, GPS receivers, and radio telescope arrays that collectively represent some of the most sensitive measurement infrastructure humanity has ever built. That duration varies, not by much in absolute terms. The fluctuations we're talking about are measured in milliseconds, sometimes fractions of milliseconds, a millisecond, 1/1000th of a second. You can't feel it, you can't perceive it, no experience of daily life would ever reveal it, but the fluctuation is real, it is measured, and it carries information about what is happening deep inside the planet, because of a physical principle called conservation of angular momentum. Here is the underlying physics, and it matters enough to explain clearly. Earth is, to a first approximation, a closed system. External gravitational forces, from the moon, from the sun, do act on it and produce tidal effects. But on the timescales we're discussing, the dominant angular momentum exchanges are internal. The total angular momentum of the whole planet, all its layers together, from the innermost solid core to the outermost wisps of atmosphere, is conserved. It doesn't spontaneously change. That means, if one internal component speeds up its rotation, something else has to slow down to compensate. Angular momentum shuffles between layers. When the inner core accelerates relative to the mantle and crust slow down slightly, and the day becomes fractionally longer. When the inner core decelerates, momentum transfers back upward, the surface layer speeds up slightly, and the day shortens. This is not a theoretical prediction awaiting verification. It has been directly observed, repeatedly, in the day-length record. Geodesists, scientists whose specialty is measuring the precise shape, rotation, and gravitational field of Earth, have been accumulating length-of-day data for over a century. The precision dramatically improved in the 1970s with the development of very long baseline interferometry. VLBI is a technique in which pairs of radio telescope arrays on opposite sides of the planet simultaneously record signals arriving from distant quasars. Objects billions of light years away, whose positions in the sky are essentially fixed reference points. The tiny difference in arrival time of a quasar's signal at two widely separated radio telescopes reveals the exact orientation and rotation rate of Earth between them, to a precision better than a milliarcsecond. With VLBI, the length of a day can be measured to within microseconds. The archive of these measurements now stretches back more than 50 years. What that archive shows is a set of overlapping fluctuations in day length, operating on different timescales. The shortest are driven by weather, large-scale atmospheric circulation patterns redistributing angular momentum across the surface as seasons change. Others are driven by ocean currents, others by the semi-annual movement of mass as ice sheets accumulate and melt at the poles. These are well understood. Then, there are the longer period fluctuations, multi-year to multi-decadal oscillations that cannot be explained by surface processes. Fluctuations that must have their origin deeper in the planet. Fluctuations that track, over decades, the internal redistribution of angular momentum between the core system and the mantle above it. Among those longer oscillations, there is a dominant pattern with a period of approximately 60 to 70 years. When Yang and Song's inner core rotation timeline, derived entirely from seismic waveform analysis, using completely different instruments, completely different physics, and a completely separate research tradition, was placed alongside the geodetic length-of-day record. The alignment was visible without requiring statistical manipulation. The periods when the inner core was measurably accelerating its superrotation corresponded to periods when the day was getting fractionally shorter, angular momentum flowing downward from the mantle into the accelerating core. The periods of inner core deceleration corresponded to periods when the day grew fractionally longer. Momentum flowing back upward as the braked core transferred its rotational energy back to the layer above it. And the most recent onset of inner core deceleration, which the seismic data placed around 2009, corresponded precisely to the beginning of a subtle but measurably real lengthening of Earth's day.
5, we have the ready to start. 2, 1, 0. Booster ignition and liftoff of Shuttle Endeavour, NASA's final space station crew compartment that brings a bay window view to our celestial backyard.
Is coupling from above. The combined gravitational and electromagnetic interaction between the inner core, mediated through the fluid outer core, acting as a
Mission
brake
Control
on the
Houston,
inner
Endeavour's
core's
roll maneuver is
eastward
complete.
spin.
It is now in a heads down
Physics of
position
this
on
coupling
track for
has
its flight
been
to the
understood
International
in
Space
broad
Station.
terms for decades. What is new is that we are watching it play out in real data, at the resolution of modern instruments, for the first time in history. One dataset, The seismic waveforms could theoretically be explained by artifacts, instrument drift, tectonic changes in source regions, complications in the data reduction pipeline.
8,
These
7,
alternatives were tested
6,
carefully
5,
by Young
4,
and Song
3,
and by independent teams.
1.
They failed.
Ignition and liftoff of Ares 1X. Testing concepts for the future of new rocket design.
Sensitivity. 2 independent datasets, seismic waveforms and geodetic day-length measurements, using different instruments, different physics, different research communities, across decades of accumulated data, converging on the same timeline and the same mechanism. That's not explainable as artifact or coincidence. And the third dataset, already out there, already published, already in the satellite archives, made any residual doubt essentially impossible to maintain. Because the magnetic field had been telling a version of this story for years. We just hadn't connected the threads. Chapter 3b. The magnetic field is already changing, and has been for decades. There is a region of Earth's sky, if you were orbiting the planet and looking down, where the magnetic field is wrong. Not slightly off, not marginally weaker, dramatically, measurably, functionally weaker than it should be, given the overall structure of the field around it. That region sits over the South Atlantic Ocean, stretching from the eastern coast of South America across to the southwestern edge of Africa. It's called the South Atlantic Anomaly, depending on which measurement you use. The magnetic field intensity in the heart of this region is less than half of what it is at equivalent latitudes on the opposite side of the planet. For satellites passing through it, that weakness is not academic, it's an engineering reality. The Van Allen radiation belts, normally held safely away from low Earth orbit by the magnetic field's pressure, dip closer to the surface here. Charged particles penetrate. Instruments absorb radiation. The International Space Station adjusts its crew schedules and systems operations when it passes through the anomaly. NASA routinely powers down non-essential components on satellites transiting the region. The South Atlantic Anomaly has existed, in some form, for at least 400 years. We can see it in the paleomagnetic records preserved in ancient lavas and sediments. But it has not been static. It has been growing, drifting westward, and since roughly the early 2000s, the growth rate has been accelerating. ESA's Swarm mission, a constellation of 3 satellites launched in November 2013, specifically to map Earth's magnetic field with greater resolution and temporal coverage than ever before, has provided the sharpest picture yet of this acceleration. The anomaly has expanded its footprint. Its western boundary has pushed further towards South America. In recent years, satellite data has suggested the anomaly may be beginning to split, developing a secondary minimum of field intensity over the African continent, in addition to the primary one over the South Atlantic. Now, here is the piece that most mainstream coverage of the 2023 core paper left out of the discussion entirely. The timing of the South Atlantic Anomaly's accelerating expansion corresponds to the period identified in completely independent seismic data as the onset of inner core deceleration. The period around 2009, the period when the seismic waveform signatures stopped progressing. The period when the length of day data shows the day beginning to lengthen. That same period is when satellite and ground observatory measurements show the rate of South Atlantic Anomaly growth beginning to accelerate. Let me be precise about what this does and does not mean, because precision matters here. Scientists have not established a proven causal mechanism linking inner core rotation changes directly to South Atlantic Anomaly behavior. The geodynamo, the system that generates Earth's magnetic field, is a complex, nonlinear, three-dimensional fluid dynamics problem. It is one of the most computationally and theoretically challenging systems in Earth science. the coupling between inner core rotation and outer core fluid dynamics, and from outer core dynamics to the surface magnetic field, is real. It's physics, it's not disputed. But the specific pathways through which a change in inner core rotation propagates into specific features of the surface field are not yet mapped with the resolution needed to prove causation. What we have is correlation. Three-way correlation across three independent measurement systems converging on the same timeline. In complex, physically coupled systems, that kind of correlation is not coincidence. It is signal. The challenge is mapping the mechanism. Some geophysicists have argued publicly that the South Atlantic Anomaly's behavior is within the normal range of geomagnetic variation. And this is technically accurate. The paleomagnetic record shows that the field has weakened and reorganized many times in Earth's history. Anomalies like the South Atlantic one have appeared and disappeared on geological timescales. On this basis, several researchers characterized the current situation as unremarkable. But there's a critical distinction between within the range of historical variation and well understood and predictable. The South Atlantic Anomaly's current rate of expansion is at the faster end of what historical records suggest. The evidence of a possible split into two minima, if it continues, would represent a more complex field geometry than anything in the recent paleomagnetic record. And the simultaneous occurrence of inner core rotation change, day-length anomaly, and field acceleration suggests that several processes may be operating in concert in a way that the "it's within normal range" framing doesn't fully capture. One anomaly can be noted and filed. Two converging anomalies start to form a story. Three simultaneous, physically coupled anomalies, all pointing at the same period in time. That's not something you explain with a normal variation. That's something you take seriously. Chapter 3, C. The 70-year cycle, and where we are in it. Here's the number that puts everything into a different frame. 70 years. That is the approximate period of the inner core's oscillation cycle, as proposed by Yang and Song's 2023 paper. The inner core spins faster than the planet above it for roughly 35 years. The superrotation phase that seismologists had been observing and measuring since the 1990s. Then it decelerates, passes through neutral, potentially reverses into subrotation, and holds that reversed phase for roughly another 35 years. Then, the electromagnetic coupling from the outer core pulls it back eastward again, and the cycle repeats. This has been happening, the models suggest, for a very long time. Billions of years, potentially, in some form or another, with the specific period shifting as the planet's internal heat gradually decays over geological time. But the rough order of magnitude, a multi-decadal oscillation driven by the balance between electromagnetic acceleration and gravitational braking, is what the current evidence supports. And when Yang and Song looked at historical datasets for evidence of a previous cycle, they found it. The data suggests that a similar inner core rotation change, a pause or reversal in the superrotation, occurred previously around the early 1970s. This is harder to see clearly than the 2009 event, because the seismic monitoring networks of the 1970s were less comprehensive, less digitally archived, and less globally distributed than what exists today. The earthquake waveform datasets for that era are patchier. But the pattern is there, at lower resolution, consistent with the proposed oscillation. And when you look at the geomagnetic record from the early 1970s, the observatory measurements, the magnetic pole position data, the rate of change measurements, there are features in that record that are consistent with what you would expect during a period of inner core rotation change. Subtle shifts in the rate of field change, anomalies in the magnetic north drift rate, changes in certain geomagnetic indices, not dramatic changes. Not changes that attracted much attention at the time, but changes that, viewed in retrospect through the lens of the 2023 paper, form a coherent pattern. This answers the third question we opened: is this part of a cycle, or something unprecedented? The honest answer is both. The cycle appears to be real. The 60 to 70 year oscillation is a genuine feature of Earth's deep interior dynamics, not a one-time event. Previous cycles have occurred. The planet has been through this before, many times, and the magnetic field has recovered each time. In that sense, the scientists who say it's a natural cycle are correct. But here is what makes this particular passage through the cycle genuinely unprecedented in human history. We are watching it happen for the first time. Every tool that allows us to know what we now know about this cycle was developed during the current oscillation period. The global digital seismograph networks that produced the waveform datasets Yang and Song analyzed were built and expanded from the 1970s onward. The GPS and VLBI geodetic networks that measure day-length fluctuations with microsecond precision reached their current coverage in the 1990s. The ESA swarm satellite constellation began providing high-resolution magnetic field maps only in 2013. Every one of these tools was built during the cycle they are now documenting. Prior passages through this oscillation happened without anyone noticing. The 1970s reversal occurred without the seismic network dense enough to detect it clearly. The 1900s version occurred before global seismograph networks existed. All of them left only faint traces in the paleomagnetic and geological record, enough to be reconstructed in retrospect, but not enough to be observed in real time. This time, we have the instruments. This time, we are watching. And watching something in real time reveals details that retrospective reconstruction never can. We are learning what this oscillation actually looks like as it unfolds, not as an averaged signal in a sediment core, but as a dynamic, evolving process playing out across multiple coupled systems simultaneously. The seismic data, the length of day data, the satellite magnetic field maps, these are all showing us different facets of the same event, at a resolution and in a time frame that no previous human civilization ever had access. The scientific community is already responding to this opportunity. ESA's Swarm satellite constellation has had its mission extended, in part because the South Atlantic Anomaly's evolving behavior has made continuous high-resolution monitoring a priority rather than a luxury. Proposals for new generation seismic arrays, one centered in the southern hemisphere, to improve coverage of the earthquake waveform datasets most useful for inner core studies, are advancing through funding pipelines with the inner core oscillation as one of the primary scientific justifications. The International Federation of Digital Seismograph Networks is expanding its global station coverage, specifically to improve the data quality that inner core rotation studies depend on. What all of these instruments are watching for is the same thing: the behavior of the current oscillation as it continues to evolve. Is the inner core still reversing its relative rotation direction, or has it stabilized? How does the outer core fluid respond as the inner core boundary condition shifts? Does the South Atlantic anomaly continue to grow and split, or does it stabilize as the oscillation progresses? Does the magnetic north drift rate continue to accelerate, plateau, or begin to slow? These questions will be answered, not all of them immediately, but within a decade. The data that currently exists in fragmentary form will be dense enough to draw clearer conclusions. The point is, we are not watching history, we are watching something happening now, in real time, with instruments sophisticated enough to see it. And that changes the character of this story from a geological curiosity to something more immediate. Chapter 3D. 3 Interpretations, and why the comfortable one may be incomplete. The scientific community, when pressed about the inner core story, tends to converge on a framing that is accurate, defensible, and leaves important questions sitting quietly in the background. Let me put all three interpretations present in the peer-reviewed literature
10,
on the table side
9,
by side,
8,
because they
7,
carry meaningfully
6,
different implications.
5. We have
and
filter ready to
choosing
start. 2,
honestly
1.
looking at
Clear.
what it does
Booster
and does
ignition
not support.
and liftoff of
The
Shuttle Endeavour
conservative
with NASA's
interpretation
final space station
the
crew
inner
compartment
core
that brings a bay window
oscillation
view
is a
to our
real,
celestial
natural,
backyard.
multi-decadal feature of Earth's geodynamics. It has been occurring throughout geological history for as long as Earth has had a solid inner core, which is somewhere
This is Mission
between
Control
half a
Houston.
billion
Endeavour's
and
roll
a
maneuver is
billion
complete.
years,
It is now
based on
heads down
estimates
position
of when
on
the
track
inner
for
core
its
began
flight to the
crystallizing
International Space
as the
Station.
planet slowly cooled from its formation. Previous cycles ran their course. The magnetic field weakened somewhat during those cycles and recovered each time. The South Atlantic Anomaly is a persistent feature that has existed for centuries and represents a normal fluctuation in the non-dipole component of the
T-minus
magnetic
10,
field.
9,
The current
8,
weakening
7,
and acceleration in anomaly
6,
growth
5,
is within the
4,
envelope
3,
of what paleomagnetic reconstructions
and
document.
ignition and liftoff of Ares 1X, testing concepts for the future of new rocket
or
design.
surface systems on any human-relevant timescale. This is the position of most working geophysicists who have commented publicly on the 2023 paper. It is grounded in a legitimate reading of the paleomagnetic record and the physical modeling of the geodynamo. It is probably broadly correct in its most important claim that Earth's field will recover, that life will not be devastated by this oscillation cycle, that the geodynamo is robust over geological time, and it glosses over several things that matter to a civilization that exists in the present rather than in geological time. The moderate interpretation adds a layer that is harder to fit into a reassuring summary, but that is explicitly discussed in the scientific literature by researchers with no axe to grind. The current oscillation is natural, but it is occurring on top of a longer-term background trend that complicates any simple comparison to previous cycles. Earth's magnetic field has been losing overall dipole intensity for at least 200 years. This trend, documented continuously since the first systematic measurements of field strength began in the early 19th century, predates the current inner core oscillation cycle and is almost certainly driven by longer-term dynamics in the outer core that operate on century scales rather than the 70-year inner core period. Separately, the slow westward drift of the magnetic field's non-dipole features, a movement that has been documented since the 17th century through careful compass measurements at fixed observatories, represents another independent long-term change accumulating in the background. The practical implication is that the current inner core reversal phase is not occurring in the same magnetic baseline environment as previous reversal phases. The field entering this part of the oscillation is already somewhat weaker than the field that entered previous corresponding phases. Whether that difference affects how deeply the South Atlantic Anomaly expands during this cycle, how far magnetic north migrates before stabilizing, how the field reorganizes itself as the inner core's rotation restabilizes, these questions are open. The existing models do not resolve them. The observational record of the current cycle does not yet span enough of it to establish the empirical answers from data alone. Several independent research groups have published papers specifically noting this compounding of timescales. It is not a minority view or a fringe concern. It is a recognized complexity that the natural cycle, nothing new, framing simply doesn't address. The structurally significant interpretation goes further still, and it deserves an honest statement rather than dismissal. A full geomagnetic polarity reversal, where the geographic north and south magnetic poles switch positions, takes thousands of years to complete. During the transitional period, the field weakens dramatically, disorganizes into a multipolar configuration with several poles forming and dissolving simultaneously, and then gradually rebuilds in the new polarity. This has happened hundreds of times in Earth's history. The paleomagnetic record preserves these reversals as transitions in the magnetization direction of volcanic rocks and sediments laid down during the reversal periods. The last full reversal, the Brun-Smatayama reversal, occurred approximately 1780,000 years ago. The field is currently overdue for a reversal by the statistical standard of average interreversal intervals. This doesn't mean a reversal is scheduled. Reversals are chaotic events driven by the nonlinear dynamics of the geodynamo, not clockwork. But it means the current geomagnetic state is not inconsistent with a field that is in the early, very slow approach to a future reversal on timescales of thousands to tens of thousands of years. No published paper asserts that a polarity reversal is imminent on a human timescale. Making that claim would be irresponsible, and the evidence does not support it. But several papers note explicitly that the current combination of features, multi-century field weakening, the scale and growth dynamics of the South Atlantic Anomaly, the magnetic pole migration acceleration, places the current geomagnetic state at a point that warrants continued monitoring rather than confident reassurance. The difference between the conservative and structurally significant interpretations is not about the science being disputed. The physics is the same, the data is the same. The difference is about what level of uncertainty is acceptable to communicate publicly, and what time frame is considered relevant for the audience being addressed. Now, let's talk about the human dimension of this story, because the science is only part of it. There is something particular about the discomfort people feel when they learn that Earth's inner core oscillates. It's qualitatively different from the discomfort of reading about an asteroid risk, or a solar storm, or even a distant earthquake fault. External threats, or threats from the surface, arrive in categories we can intuitively understand. The inner core unsettles differently, because it is the center. We carry, mostly without articulating it, a deep assumption that centers are stable, that what lies at the heart of a system is more permanent than the edges, the reliable anchor around which everything else changes and moves. The atmosphere is volatile by definition. The crust shifts, we have accepted plate tectonics. The surface is, in a sense, permitted to be unreliable, but the core, the iron ball at the middle of everything, that felt, without anyone needing to say it, like the definition of foundational, and it isn't. It oscillates. It couples to the fluid above it and the field above that. It transfers angular momentum upward through layers of iron and rock. It changes its rotational state on human-relevant timescales, not geological timescales, not astronomical timescales, but timescales of decades. Timescales on which civilizations build infrastructure, calibrate navigation systems, and develop engineering standards. We assumed stability because we had a model that worked within the precision available to us. The model was right as far as it could see. What the improved precision of modern instruments revealed is that there was more happening than the model had access to, not because the modelers were wrong, but because the measurement capability was there yet. This is the normal situation in science. But it's a hard truth to sit with when the thing that turned out to be more complex than expected is the center of the planet you live on. Oumuamua, in the previous video in this series, demonstrated the same principle from the outside. From 85 million miles away, a single measurement revealed that the category we had prepared for interstellar objects didn't quite contain the object that actually arrived. The inner core demonstrates it from directly beneath us. The category we built for the center of the Earth, stable, foundational, essentially permanent on human timescales, turned out to be a simplification. A simplification that was invisible until our instruments became sensitive enough to see past it. Same lesson. Two completely different directions. One question emerging from both. What else are we assuming, without realizing we're assuming it? So, after everything we've covered, the seismic waveform record, the angular momentum exchange in the day-length data, the South Atlantic Anomaly satellite measurements, the historical oscillation pattern, and its prior precedent. The question is no longer whether something meaningful is happening in Earth's deep interior. The question is what it means that we are the first generation in history with instruments sensitive enough to watch it happen in real time. And that question leads directly to what comes next. Remember what we asked at the very beginning of this video: what happens when the engine at the center of Earth changes gear? We've spent the last 30 minutes building the evidence layer by layer, the seismic waveforms and what they revealed about a halted rotation, the angular momentum transfer and what the day-length data showed about the coupling mechanism, the South Atlantic Anomaly, and what satellite observations showed about the magnetic field's response, the historical oscillation cycle, and what it revealed about the scale and nature of what we're observing. Now, let's put the full picture together and look at the parts that almost never appear in the coverage you've already seen. The mainstream reporting on the 2023 Yang and Song paper followed a pattern that science journalism often falls into when dealing with results that are simultaneously significant and technically nuanced. The most reassuring available framing goes into the headline. The technical complexity goes into paragraph 4, if it appears at all. Scientists discover Earth's inner core has stopped spinning, but say it's just a natural cycle. That was the version of this story most people encountered. And, as I said earlier, accurate as far as it goes. Here is what the paper actually contains that didn't make those headlines. First, the uncertainty bounds on the rotation measurement are larger than most coverage implied. Yang and Song are explicit about this in the paper. The data clearly shows a change in the differential seismic signature, consistent with rotation deceleration and probable reversal. What the paper does not do, because the data cannot support it, is precisely constrain the magnitude of the reversal, the exact year it began, or whether the reversal is still actively ongoing or has reached a new equilibrium state. The confidence intervals on those specific questions are significant. The certainty with which some headline writers described a stopped and a reversed core was a simplification of what the paper actually claims. Second, the 2023 paper is not the final word from the seismological community, and it is not universally accepted as correct in its specific conclusions. Several independent research groups, teams in the United States, in Germany, in Australia, have published their own analyses of inner core rotation using different earthquake datasets, different methodological approaches, and different assumptions about the inner core's structure. Some of those analyses produce results broadly consistent with Yang and Song. Others produce results that are harder to reconcile with a clean, regular, 70-year oscillation. The seismic evidence for inner core rotation behavior is genuinely contested within the field. Not in a fringe versus mainstream sense. All of these are credible, published, peer-reviewed teams. In the a difficult measurement, different approaches, different answers sense that is entirely normal for frontier science operating near the limits of what current data can resolve. Science journalism rarely conveys this kind of internal uncertainty well. A contested result reported as a clean discovery, a range of interpretations presented as a consensus. Its understandable complexity is hard to communicate in a headline, but it produces a public picture of scientific knowledge that is tidier than the actual state of the field. Third, The correlation between inner core rotation timing and geomagnetic field behavior is real and documented in multiple independent papers, and it currently has no proven mechanistic explanation in the form of a model that predicts specific field changes from specific rotation changes. The physics of how the inner core couples to the outer core and from the outer core to the surface field is understood in broad strokes. The details, which coupling mechanisms dominate on which timescales, how changes propagate through the highly turbulent outer core, how the surface field responds to boundary condition changes at the inner core, are active research questions without settled answers. The geodynamo modeling community has made remarkable progress in the last 2 decades. Numerical simulations of the geodynamo now reproduce many features of Earth's real magnetic field with impressive fidelity. But those simulations run at parameter values that differ from the real Earth by orders of magnitude in several key quantities: fluid viscosity, magnetic diffusivity, rotation rate, because the real values are computationally inaccessible. What the simulations tell us about the specific behavior of Earth's real geodynamo during an inner core rotation change is constrained by those limitations. We have a plausible coupling
T-minus 10,
story.
9,
We do not
8,
have a predictive
7,
model.
6,
Four.
5, we have to go for radio start, 2, 1, 0, booster ignition, and liftoff of Shuttle Endeavour with NASA's final space station crew compartment that brings a bay window view to our celestial backyard.
Ever observed with modern instruments, previous reversals of the inner cores, differential rotation, high precision seismic networks, satellite magnetometry,
This is Mission Control Houston. Endeavour's roll maneuver is complete. Now heads down position on track for its flight to the International Space Station.
From the paleomagnetic record, we know the field recovered. We don't know what the field looked like in detail during those previous transitions, whether the weakening was gradual or punctuated, whether specific geographical anomalies appeared and resolved, how the geodynamo reorganized itself through the rotation change.
T-minus
We are
10,
writing that
9,
template now.
8,
Every
7,
year that swarm satellites
6,
continue
5,
operating,
4,
every
3,
earthquake pair
2,
added to the
1.
waveform dataset.
Ignition and liftoff of Ares 1X. Testing concepts for the future of new rocket design.
Looks like from the surface. Future geophysicists will have data that current ones can only wish for. Future models of the geodynamo will be constrained by observations that don't yet exist. It's a natural cycle, nothing to worry about. Framing is not wrong. It is incomplete, and the incompleteness matters, because the next dataset that will allow us to say something more precise depends on continuing to observe the current event rather than declaring it understood. Now, let's talk about something that received almost no attention in the popular coverage of the inner core story, but that directly affects every person who uses a smartphone, boards an airplane, or relies on any navigation system. Magnetic north has been moving, not philosophically, not in some abstract geological sense, in the literal, navigational, turn-by-turn directions sense. The geographic location on Earth's surface where a compass needle points, the magnetic North Pole, has been physically migrating across the planet's surface since humans first started measuring its position systematically in the 19th century. When those first measurements were made, magnetic north was over northern Canada, in the region of what is now Nunavut. Over the following century and a half, it drifted northward and westward at a rate of roughly 15 kilometers per year. Manageable, slow enough that navigation charts and magnetic declination tables could be updated on a routine schedule without urgency. Then, in the 1990s, something changed. The drift rate began accelerating. Through the 2000s, it reached 30, then 40 kilometers per year. By the 2010s, magnetic north had crossed the Canadian Arctic, tracked over the geographic North Pole, and was heading towards Siberia at more than 50 kilometers per year. The drift direction had also shifted. The curved path through the Canadian archipelago gave way to a more direct trajectory aimed at the Russian Arctic. The speed of magnetic north's migration had more than tripled in the space of 3 decades. The system that tracks this and adjusts global navigation to account for it is called the World Magnetic Model. It's a mathematical description of Earth's entire magnetic field, maintained jointly by NOAA in the United States and the British Geological Survey in the United Kingdom, and updated on a 5-year cycle to account for field changes. Every smartphone GPS, every airline navigation computer, every ship's compass system, every military guidance application on the planet uses the World Magnetic Model as its magnetic reference. It's infrastructure in the truest sense, invisible, foundational, and taken entirely for granted until it fails. The 5-year update cycle was designed around a magnetic field that changes at a manageable rate. The 2015 update was issued on schedule, with no unusual urgency. The 2020 update was likewise routine. But in February 2019, NOAA and the British Geological Survey issued an emergency unscheduled update to the World Magnetic Model. That had never happened before. Issuing an out-of-cycle update requires that the field has drifted far enough from the model's predictions that navigation systems relying on it are accumulating errors beyond what the specifications allow. The 2019 emergency update was triggered specifically because magnetic north was moving faster than any prior model had predicted. Fast enough that compass applications on phones in certain high-latitude regions were beginning to point in measurably wrong directions. The acceleration in magnetic north's drift rate, the acceleration that eventually triggered that emergency update, occurred on a timeline that corresponds directly to the inner core deceleration period identified in the seismic data. This is not a connection that the agencies involved have emphasized publicly. It's a connection that several research papers have identified, and that is now an active area of investigation in the outer core dynamics community. The relationship between changes in inner core rotation state, changes in outer core fluid flow patterns, and changes in the migration rate of the magnetic pole is being studied. The mechanism is not proven. The correlation is documented, and the practical implication is sitting right there in the fact of that emergency update. The infrastructure that global navigation depends on required an unscheduled intervention, because the field was changing faster than expected. That has happened once in the history of the World Magnetic Model. It happened during the period when the inner core was changing its rotation state. Let me put the future implications of all this in concrete terms, because the abstraction of a magnetic field changes can obscure what that actually means at the surface level. Power grids are sensitive to geomagnetically induced currents, currents that form in long transmission lines when a changing magnetic field induces voltages across their length. The same way a changing magnetic field through a coil induces voltage in an electrical generator. During major geomagnetic storms, when the solar wind compresses the magnetosphere and drives rapid field changes, those induced currents can overwhelm protective equipment and damage transformers. In March 1989, a geomagnetic storm that was significant but far from the historical maximum caused a 9-hour total blackout across the Canadian province of Quebec. 6 million people, 9 hours. Transformers that took months to repair or replace. The relevant variable here is not the intensity of solar storms. The sun doesn't care what Earth's magnetic field is doing. The relevant variable is the strength of Earth's magnetic shield during a solar event. A weaker shield means larger induced currents for the same solar input. The field is weaker now in the South Atlantic and globally than it was in 1989. satellite navigation systems are calibrated to a field model that required an emergency update in 2019. The question of whether the future update cycle, currently 5 years, will remain adequate as the field continues to change is under active review. Moving to faster update cycles requires more frequent model recalibration, which requires continuous high-precision monitoring, which is exactly what swarm and ground observatory networks are designed to provide. High-frequency radio communications, used by aviation, maritime operators, military systems, and emergency services, propagate through the ionosphere, the upper layer of the atmosphere that is shaped and structured by interaction with the magnetic field and incoming solar radiation. A changing magnetic field changes ionospheric structure. A more variable ionosphere affects radio propagation. These effects are small in ordinary times and potentially significant during geomagnetic disturbances. None of these systems were designed with a shifting inner core rotation cycle in mind. That's not because the engineers were negligent. It's because the knowledge we now have about the inner core oscillation did not exist when those systems were designed. We have known about the inner core's superrotation for less than 30 years. We have had high-precision evidence that the rotation can reverse for less than 5 years. The engineering standards, the update intervals, the risk models, all of these were established in the context of a magnetic field that was assumed to be more stable than it has proved to be. The work that needs to happen now is the recalibration of those assumptions. The swarm mission extension reflects that. The expanding seismic networks reflect that. The increased update frequency of geomagnetic models reflects that. The field is not in crisis. The situation is not an emergency. But it is a system behaving in ways that were not fully anticipated, and the appropriate response is exactly what is happening. More measurement, better models, more frequent calibration of the infrastructure that depends on knowing where the field is. And here is the thing that stopped me cold when I was putting this video together. The inner core oscillation cycle, approximately 70 years from peak superrotation back to peak superrotation, is almost exactly the span of modern global technological civilization. Let that sit for a moment. Global aviation infrastructure was established in the 1940s and 1950s. International civil aviation standards, intercontinental routes, navigation protocols, all built in the post-war decades. Satellite communications began in the 1960s. GPS navigation became operational for civilian use in the 1980s. The global internet achieved genuine planetary connectivity in the 1990s. Mobile communications reached most of the world's population in the 2000s. Every single layer of the interconnected technological infrastructure that every modern society depends on. The infrastructure that allows food distribution systems to function, that allows financial systems to operate, that allows emergency services to navigate, that allows aircraft to find their way across oceans, was built during a single inner core oscillation cycle. And more specifically, the overwhelming majority of it was built during the superrotation phase of that cycle, the first 35 years, when the inner core was spinning eastward faster than the planet, when the magnetic field was more stable than it currently is, when the World Magnetic Model's 5-year update cycle was more than adequate to track the field's gradual evolution, when the concept of an inner core oscillation didn't exist in any scientific paper, anywhere. The infrastructure was designed for a world that was in one phase of a cycle. It is now operating in a different phase of that cycle. And the two phases don't have identical characteristics for the things the infrastructure depends on. We have never run a globally connected technological civilization through a complete inner core oscillation. We are doing it for the first time, right now, in this decade. The power grids, whose vulnerability to geomagnetically induced currents was assessed against storm events that occurred in the stable phase. The satellite navigation systems, whose update intervals were set when the magnetic pole was drifting at 15 kilometers a year, not 50. The telecommunications satellites, whose radiation hardening specifications were based on Van Allen belt geometry, associated with a stronger magnetic field. The high-frequency radio propagation models that aviation and maritime navigation rely on, built around ionospheric behavior in a different geomagnetic baseline. None of it was designed wrong. None of it was negligently built. The engineers who made those specifications used the best available information about the magnetic environment. The problem is that the best available information didn't include the fact that the environment was about to enter the second half of a 70-year oscillation cycle that the first half's designers couldn't have predicted. This is what it looks like when civilization is younger than the cycle it's living through. We are not in danger. The transitions are slow. The changes are measurable in milliseconds and fractions of a percent. Nothing about this produces a catastrophe on a human timescale or in any near-term planning horizon. But not catastrophic, and it doesn't require attention, are different things. The Emergency World Magnetic Model update in 2019 required attention. The Swarm mission extension required attention. The expanding seismic monitoring networks require funding and attention. The ongoing research into geomagnetically induced current risks in long-distance power transmission infrastructure requires attention and engineering work. These are the responses of a civilization that has noticed, belatedly, partially, but genuinely, that it is living through a geological process it was never designed for. And the appropriate response to that recognition is exactly what is happening. Better measurement, more frequent calibration, more honest engineering risk assessment, and ongoing scientific investigation of a process we are observing in real time for the first time. We are flying through weather we have never experienced before. In a plane we built before we knew the weather existed, and now we know.
T-minus 10,
There is
9,
one more
8,
piece to this story.
7,
Something we
6,
haven't touched today.
5, we have to go from ready to start, 2, 1, 0, booster ignition, and liftoff of Shuttle Endeavour with NASA's final space station crew compartment that brings a bay window view to our celestial backyard.
Multiple poles forming and dissolving simultaneously. The field dropping to a small fraction of its original intensity for centuries. And what happened to life on Earth
This is
during
Mission
those
Control
periods?
Houston. Endeavour's roll
Particularly,
maneuver is
the
complete.
biological
Now
record
heads down
around the
position
last
on
known
track for
major
its flight to the
geomagnetic
International
excursion,
Space Station.
roughly 42,000 years ago, is a question that the scientific community is only beginning to take seriously as a connected story. We'll be connecting those dots next time. That is where we go next. Tonight, we didn't just learn about a sphere of iron rotating at the center of a planet. We discovered that something we had
T-minus
taken
10,
completely
9,
for granted,
8,
the engine
7,
at the center of this world,
6,
the process
5,
that has been
4,
generating
3,
Earth's magnetic
2,
shield for billions
1.
of years.
Ignition and liftoff of Ares 1X. Testing concepts for the future of new rocket design.
The sensitivity threshold of every instrument we had until very recently. Quietly and consistently, on its own timescale, independent of whether anyone was watching. And the first time we developed instruments precise enough to observe it clearly, what we found was not the stable, reliable baseline we had assumed. It was a dynamic system in mid-oscillation, a system that couples across layers, exchanges angular momentum, responds to the competition between electromagnetic torque and gravitational restoring force, and periodically shifts its rotational state in ways that propagate upward through thousands of kilometers of material to produce measurable effects at the surface we live on. That's a very different picture from the fixed, foundational inner core of the textbook diagram. And the gap between those two pictures, between the diagram and the reality, is worth sitting with before we close, because it reveals something important about how knowledge actually accumulates and where assumptions hide. What remains genuinely unresolved about this story deserves to be stated clearly, rather than papered over with reassurance. The precise rotation state of Earth's inner core right now, whether the reversal is still ongoing, whether it has stabilized at some new differential rate, what magnitude the data actually supports, is contested between seismological teams working with different datasets and different methodologies. The 2023 paper proposed a specific oscillation model with specific timing. Independent teams have produced analyses that range from broadly consistent with that model to harder to reconcile with it. The measurement problem is genuinely at the frontier of what the available earthquake waveform archive can resolve. The causal chain linking inner core rotation changes to specific surface magnetic field behavior. The South Atlantic Anomaly's accelerating growth, the magnetic pole's rapidly increasing drift rate, is a documented correlation without a proven mechanism at the level of specificity that the geodynamo modeling community would consider validated. The broad physics connects these components. The quantitative model that predicts specific field changes from specific rotation changes, with the precision needed to say, this rotation change caused that field feature, does not yet exist in a confirmed form. We have one previous inner core oscillation cycle captured in any data at all, and that capture was at substantially lower resolution than the current one, because the instruments of the 1970s were considerably less capable than those of today. We cannot confidently assert whether the current cycle is behaving the same way as the previous one, because the previous one's record isn't detailed enough for a rigorous comparison. And crucially, we have never run any kind of sophisticated global technological infrastructure through one complete inner core oscillation cycle before. The answers to what the surface effects of a core reversal look like at the resolution of modern measurement can only come from watching the current cycle play out in real time. That empirical record will be far more useful to scientists and engineers 2 or 3 generations from now than any model or paleomagnetic reconstruction currently available. The honest position: we are observing something ancient for the first time with modern eyes. We are in the early stages of understanding what we are seeing, and that is not a failure. That is the leading edge of what knowledge looks like when measurement capability improves faster than interpretation can keep up. There are things this story has taught me about how knowledge accumulates, and where assumptions live, that go further than any specific result about seismic waveforms or magnetic field models. The first is this: the things we assume are fixed are almost always the things most worth examining. For centuries, Earth's deep interior was treated as foundational in a way that made the assumption invisible. No one sat down and decided to assume the inner core is stable. The assumption was simply never contradicted, because the instruments capable of contradicting it didn't exist. The models built on that assumption worked. They predicted everything the available measurements could test. And so, the assumption became invisible, a floor beneath the models rather than a choice within them. The first time the measurement precision improved enough to test it, the assumption was gone. What remained was more complex, more dynamic, and more interesting. The second, instruments don't just answer existing questions, they reveal questions we didn't know to ask. The global digital seismograph networks deployed in the 1970s and 1980s were built to study earthquake mechanics, tectonic plate motion, and the risk of specific fault zones. Nobody designed them to detect inner core rotation. Nobody planned for Zhejiang to sit down with 50 years of earthquake waveform data from the South Sandwich Islands and find an oscillation in the center of the planet. That discovery emerged from the data when the data was dense enough and well calibrated enough to show it. Discovery in science often works this way, not by going where you aim, but by going where the precision finally takes you. The third, in physically coupled systems, correlation across independent measurement types is not noise, it is signal. The convergence of the seismic inner core timing, the geodetic day-length record, and the satellite magnetic field acceleration on the same period. Three independent measurement systems, using three different physical principles, in three different research communities. That convergence is telling us something real. The mechanism is not yet fully mapped. The physics that would explain exactly how the coupling propagates is a work in progress. But in a system where the components are physically connected by electromagnetic force, gravitational coupling, and fluid dynamics, three independent measurements pointing at the same period is not coincidence. It is an arrow. Science follows the arrow. The fourth, knowing that a process is natural and cyclical does not answer the question of what its consequences are in a context that previous cycles never encountered. The field has recovered from previous inner core oscillations, is a real and important geological fact. It tells us that recovery is physically possible, that the geodynamo is robust over geological time, that Earth's magnetic protection has persisted through many such cycles without catastrophe. What it doesn't tell us is how recovery looks when the infrastructure sitting above the recovering field was built during the previous stable phase and was never designed for the transitional one. The geological fact and the engineering question are different questions. The geological record answers the first. Only real-time observation of the current cycle, combined with honest engineering assessment, can answer the second. The fifth, and this one stays with me the most. Being the first generation to observe something that has happened many times before is not a footnote. It is a position of genuine privilege. In the original sense of that word, a special access, a specific advantage. Every generation before ours moved through inner core oscillation cycles without instruments sensitive enough to see them in progress. The 1970s reversal left traces. The 1900s one left fainter traces. The earlier ones left only the broadest strokes in the paleomagnetic sediment record. We are watching the current cycle in high resolution, in real time, across multiple coupled systems simultaneously. What we document about how this transition unfolds, how the seismic signatures evolve, how the day-length record responds, how the magnetic field reorganizes, that documentation will be available to every scientist who studies this problem after us. We are, right now, creating the empirical baseline that future understanding will build on. That's not a small thing to be doing. A few questions I'll leave with you. How many other assumptions about stability, about permanence, about the reliability of systems we have measured only briefly in historical terms, are we currently carrying without recognizing them as assumptions rather than facts? Earth's inner core was being measured for 150 years before the instruments became precise enough to reveal its oscillation. What other systems are currently in that position, being modeled with sufficient confidence to build infrastructure on, but not yet measured with sufficient resolution to see the structure that will eventually revise the model? What does it cost, in engineering work, in recalibration, in updates to systems designed around earlier assumptions, when the world turns out to be slightly more complex than the best available model predicted? Not a crisis, not a failure. Just the ongoing, practically important work of catching up when reality offers more detail than the previous generation of instruments could resolve. How do we build systems that handle that kind of revision more gracefully, that are designed from the start to accommodate a more dynamic world than the first measurements suggested? And does knowing that Earth has been through this before, that previous oscillation cycles ran their course, that the field recovered, that life continued through all of them, make you feel better about the current one? Or does it make you ask, What did those previous transitions actually look like in the high-resolution detail we can only now apply? If something in this video changed how you think about the ground beneath you, about the assumptions we build civilization on, about the gap between our models and the complexity they're simplifying, tell me in the comments. Which part stayed with you? The seismic technique, the emergency world magnetic model update, the 70-year civilization overlap, the South Atlantic Anomaly satellite data. I read every one of these, and they genuinely shape what comes next on this channel. If you're new to Galaxy Pulse, this is what we do here. Past the headline, past the reassuring summary, into the part of the science that deserves more time than a news cycle can give it. Subscribe. The next video connects this story to something in Earth's paleomagnetic record that the inner core oscillation has been quietly pointing toward for years. Something that has puzzled researchers in multiple fields simultaneously, and that nobody has assembled into one place quite the way we're about to. I'll see you there. Sometimes the real discovery isn't what we found, it's the certainty we lost.